Welcome to this flash talk. I'm going to give you a brief overview of our analysis of the neural population dynamics during human object vision that reveals two types of representational echoes that reverberate across the visual system. Okay, let's dive in. The primate visual system is highly recurrent. This means that information is flowing in feed-forward, lateral, and feedback directions. The question now is, in order to understand the neural population dynamics going on in the visual system, we need to understand how this communication dynamically shapes the representations across the system. How do we approach this question? We combine representational similarity analysis with temporal generalization. For this, we make use of MEG signal that was recorded during an object viewing task and source project this signal into 180 regions of interest per hemisphere. This allows us to compute a full representational dissimilarity matrix for every time point of the stimulus presentation epoch. Coming from there, we can compare the resulting RDMs between all different time points, which results in such a cross-temporal dissimilarity matrix that you can find here for the early visual region V2. Here displayed as the grand average of all subjects, and here in the bottom you can find it for 3 exemplar subjects. What one directly notices here is a higher similarity, for example, between representations during the stimulus presentation compared to, for example, those following the stimulus presentation. So, to sum up, the cross-temporal dissimilarities compare representations over time. What observations linked to recurrence can we make here? In respect to this, we observe two types of repetitive responses that we are going to call echoes. First, one can notice these diagonal lines here that are in parallel to the main diagonal of the matrix. These lines reappear in a frequency of approximately 10 Hertz, and we are going to call these diagonal echoes in the following. But they are not the only signature that we can notice here. A bit more subtle in this visualization, we can find these vertical lines here, and they seem to be a reoccurring similarity between representations following the stimulus presentation to those during the stimulus presentation. This echo signature we are going to call vertical echoes. They appear in a frequency band between 10 and 30 Hertz. Okay, so we observe these two types of representational echoes. Let's have a closer look at them to better understand what's going on. And we start with the diagonal echoes. If we compute the intensity of the diagonal echoes for all of the 180 regions in that we have separated the cortical map, we can see that they are very intense in the early visual cortex and also in more parietal regions of the cortex. If we now want to better understand what's going on with the diagonal echoes, we have to find out whether they are related to stimulus information or more linked to some ongoing oscillatory process in the cortex. In order to find this out, we can apply cross-validation techniques and compare the cross-temporal dissimilarities between different presentations of the same stimulus object. Okay, if we now look at the cross-section of this diagonal echo pattern here, we can indeed see that the cross-validation procedure does strongly diminish the diagonal echo signature. From this, we conclude that the diagonal echoes are not stimulus locked. What else might they be linked to? If we compute the intensity of the alpha power in the neural population activity prior to the stimulus presentation, we can see that this intensity does strongly predict the diagonal echo intensity following the stimulus presentation. Amongst other observations, in our hands, this leads to the conclusion that the diagonal echoes appear to be in line with traveling alpha waves that are dominant in the occipital cortex and beyond. So let's have a look at the vertical echoes. If we now look at the topography of the vertical echoes, we can see that they are also strongest in early visual cortex regions. And in addition to that, they exhibit a smooth gradient of decreasing echo intensity into other regions of the cortex, as for example, more frontal regions. If we now look at the cross-section of these vertical echo pattern, especially in respect to the cross-validation procedure that we applied, we can see that the echoing pattern is still present after the cross-validation procedure. From this, we conclude that the vertical echoes seem to be in fact driven by stimulus-locked neural responses. This means that what is echoing there seems to be stimulus-related information. Okay, let's sum this up. In this project, we identified two different types of representational echoes. They are different on many levels, as we can see here, for example, in the difference of the topography of the intensity of these two echo signatures. First, we have the diagonal echoes. And these we interpret to be linked to oscillatory responses that are ongoing in the cortex that add to the stimulus-related computations, but are themselves not stimulus-related. Second, and finally, we have the vertical echoes. These we interpret to be stimulus-locked representational echoes that are in line with a system that repetitively falls back to stimulus-related information long after the bottom-up signals via the stimulus input have disappeared. Finally, I would like to thank my two supervisors, Tim Kietzmann and Peter König, as well as our external collaborator, Kriegeskorte, and would like to invite you to reach out and discuss this research with us. And thank you very much for your attention.